A course in paleomagnetism. Hello my gems and welcome to Geocape. My name is Asha, I'm a geologist living in Norway. We are starting a new course about paleomagnetism. If you look at my channel, you will notice I already have quite a lot. I have a playlist about paleomagnetism. It's a near and dear subject to me. And if you want the short version of this, I have a mini-series with 2 episodes. But this series is going to be a bit longer. Not totally sure how long, but longer. Today we are starting off with some of the main terms and concepts. Some we have gone through before, but never bad with a little fresh up. So grab a cup of your favorite drink and let's see what's in the cave today. We will start with the magnetic field, and much like the gravitational field, it isn't something we can see or touch directly. However, we can observe its effects by studying how it impacts various objects. For instance, we can look at the magnetized metal pieces, natural magnetic rocks like the lodestone, or temporary magnets such as copper coils with electric currents. From these observations, we notice that the magnetic field is a vector field, meaning it has both direction and magnitude. We can see the magnetic field create lines, and the density or how close the lines are together gives us the magnetic flux density, often represented as B. The magnetic field strength relates to the magnetic flux density with this equation here, where mu is the magnetic permeability and m is the magnetization. The magnetization I will talk about a bit later. Another interesting thing is that when an electrical current flows through a wire, it generates a magnetic field. And if you flip the coin, the motion of the magnetic field induces electrical currents in a nearby wire. Now we will talk a bit about the magnetic moment. And when you want to define the magnetic moment, you can do it in 2 ways. By how the magnetic objects react to magnetism, and by how the electrical current makes magnetic fields behave. First, imagine a magnetic rod. The magnitude of the charge multiplied with the length of the rod gives the magnetic moment. Secondly, consider a circular loop carrying electrical current. The area of the loop and the unit normal vector multiplied together gives the magnetic moment. So now let's dive into magnetization. And magnetization is actually just a normalized magnetic moment. Normalized is when you have a vector and you normalize it by dividing it by its magnitude. There are 2 main types of magnetization: induced magnetization and remnant magnetization. First, induced magnetization is when material interacts with the magnetic field. The relationship between the induced magnetization and the magnetic field is given by this equation here, where C is the magnetic susceptibility. It can be thought of as the magnetizability of a substance. For most material, the magnetization is parallel to the magnetic field, but some are anisotropic. The remnant magnetization is like a magnetic time capsule. Imagine a material that retains a memory of the past magnetic field. It occurs when a magnetic mineral records the geomagnetic field direction at the time of the rock formation. Another thing we talk about in paleomagnetism is the Geocentric axial dipole model, also called the GAD model. And it is when a magnetic field produced by a single magnetic dipole right at the center of the Earth perfectly aligns with the rotation axis. So now, how is the magnetic field produced here on Earth? First, imagine you have a copper disc spinning on a metal axle. There's a magnetic field pointing straight up through this disc. As the disc spins, the electrons in the copper feel a force, here called the Lorentz force, that pushes them outward. This force is like what you feel when you spin around and your arms get pulled outward. These moving electrons create an electrical current that flows from the center of the disk to the edge. This current then strengthens the original magnetic field, making it even stronger. This setup is called a self-existing dynamo because this spinning disk keeps the electrical current going, which in turn keeps the magnetic field alive. As long as the disk keeps spinning, the magnetic field and the electrical currents sustain each other. So essential elements of a self-existing dynamo include a moving electrical conductor, represented by the rotating copper disc in this example, an initial magnetic field. So you can look at the Earth as it has a giant self-sustaining magnetic generator inside it. This generator works because the liquid metal in the Earth's outer core moves around. These movements create and maintain the Earth's magnetic field, even though some of it gets lost over time. To keep the magnetic generator running, a lot of energy is needed, about 10 to 13 watts, which is a huge amount. The energy likely comes from the Earth's core slowly cooling down. The outer core is freezing and the inner core is growing. So that's it for today. It was one of the long ones. I hope you had as much fun as me. If you have any questions or insights, anything at all, leave a comment down below. Tune in next week for more paleomagnetism and have a rocky day. Of course.